to my watch. Time to get started. You know, Eric just asked if I wanted him to kick things off or if I could do it. And, you know, James made a big deal about the fact that you were going to come in here to kick us all off. But, you know, I'm not shy about getting us going. So here we are. Here we are. Thanks for coming back from lunch. We are here to talk about the operations aspects of flexible loads. We heard about we had an intro this morning. We talked about the planning aspects before lunch. I don't know about y'all, but one of the things I picked up on in that planning discussion was a comment, excuse me, a comment from one of the panelists who says, you know, I used to be in operations planning, and now I'm in planning. And, you know, planning works on this stuff, and then we hand it over to operations where all the hard decisions are made. So, you know, that's what we're here for, is to figure out how those hard decisions are going to get made, how those hard actions are taken. The rubber meets the road in operations. And we talk about operations for flexible interconnection. I'm not going to be able to help myself but to bring in some of the market related aspects of that, because what are we trying to do? We're trying to ensure efficient, reliable electricity for consumers. Markets are a very strong way of doing that. So I'm joined today by a great panel. We have a balance of ISOs, Yasser Bahbaz from SPP, and then Luke Butler, who's just in the clouds, according to his picture. Luke from ERCOT, two RTOs who are maybe a little farther ahead, I dare say, in terms of managing some of the large load issues, are doing it in a little different way. So we'll hear a little compare and contrast from that. And then I'm really very excited about the customer aspect of this. So Michael from Emerald AI is here. And then Gabe Tabak gets all of our appreciation for being a last minute fill-in. But I know he's going to be great in providing that customer perspective from Verrus as well. So I wanted to give a shout out for the ESIG's Large Load Task Force and the work. I had the pleasure of working with Eric on the white paper that hopefully we'll see this month in terms of, you know, market design and operations impacts. That white paper includes 20 recommendations. And let me read them to you all right now. No, I'm kidding. One of the couple of things I wanted to pick out the two biggest and best pictures from that report, because I was waiting for somebody to say this earlier today, and I think Eric stole it from somebody else, and I'm going to repeat it again. Flexibility without coordination may be worse than no flexibility. So when we talk about flexibility, yeah, that's the moving of load in response to things, but doing it in an uncoordinated, unplanned manner, it can be problematic. And teed up here are two pictures, and I'm not one to use the word price chasing. I like responding to pricing incentives it may be a better way of saying that, but the trade-offs between kind of that, we use the term in the paper, open loop, closed loop kind of response. You know, are loads actively participating in a market, actively expressing their willingness to pay, or are they seeing a price and reacting and responding? And there are benefits and potential risks of both of those, or costs of both of those. And that trade-off is something ahead of us as well. I also like I also like this picture. I just like the picture, frankly. But the trade-off between, is that flexibility by demand? Is that just less demand? You know, making demand lighter, as shown on the right side, or is it viewed as a supply? increasing the supply as shown on the left side. Both ways count mathematically, but frankly have some operational issues. And if we wanted to dig down into cost allocation, which we're not, can also have cost allocation impacts as well. So with that kind of teeing up the run of show, if you will, we're going to start, get my words out. We're going to start with Michael, Emerald AI. He's going to give us some examples of what they've been able to do with their product and their capabilities in the UK. We're going to then move to Gabe, who will give us another kind of customer perspective, and then we'll switch to Luke and Yasser to hear the RTO perspective. I would particularly ask Yasser and Luke, as the customer guys are talking, if you have specific questions or reactions kind of right after them, let's hear those right after, and then vice versa as we move forward. So with that, I'm going to turn it over to you, Michael, and we'll get going. Thank you.
Hello? Okay, awesome. Thank you so much for that introduction. Appreciate the opportunity to share a little bit about Emerald AI and some work that we've recently done via demonstration in the UK. To get us started, I'm just going to give folks a little bit of context and background about Emerald as AI in particular, if you're not familiar. In short, our software, our platform makes an AI data center power flexible. The reason why that is so important, and probably don't need to tell this room, is of course we often only use our grid at that maximum capacity in those few hours, a few times a year. So on those really hot summer days, on those really cold winter mornings. So if you can shift power demand even by those few hours, you just get much more efficiency out of the grid. That's exactly what Emerald AI is focused on. I think also much of today is focused on. It's also focused particularly at that AI data center. And you see that not just only in our product, but also in the team itself. Sort of an intersection between AI and energy folks. For instance, our CEO comes from a long background in the energy space. I myself come from the energy space, whereas our chief scientist, our head of engineering, their careers are very much on the compute side. It's also reflected across our investors, our advisors, and across employees in the company. And it's also important to just, I think, cement and articulate the reason why. And this is true both for Emerald AI and then demand flexibility more broadly. If enabled, if part of the stack, if a lever available to the grid, demand flexibility affords at least three very important benefits. One, right, is if you're using more of the grid you already have, then you're able to bring on load more quickly, either faster interconnection, upsize interconnection. Put simply, there's an access benefit. Second, of course, if you're able to use not only generation in balancing the grid, but also demand, that provides a lever for the grid operator, and that should help to further and enhance reliability at the end of the day. And finally, because you're utilizing more of the grid you have, because you're increasing the efficiency, right? This is not just an economic term, but it has real world benefit. That should drive affordability outcomes in the future as well. So that's the context. A little bit about our deployments to date. Bless you. We have completed 5 different commercial demos and a variety of different geos. Later this year, we'll have a roughly 100 megawatt flexible facility up and running in Manassas, Virginia. Of these 5 demos, I'm going to focus in particular on the UK one today, in part because this one was relatively recently the subject of a paper, which I can make available in the show notes later, but it goes into further detail and depth to what I'm about to describe. Like all of the demos, the focus is on testing the technology itself, which again is to make a data center power flexible. So it's going to run through a variety of different scenarios and simulations. So the grid operator, in this case, that's National Grid, sending signals to the data center. So here, partners Nebius, EPRI, and NVIDIA as well, asking for some form of curtailment in real time. There are a number of different capabilities that we tested this time. So you reflect there from the fact that it's a live grid submission, right? There's nothing here where we at Emerald or the data center knew in advance what was coming. And a response that was real time. In other words, as the signal came in sub-minute, certainly response time, the data center is interacting with that request and responding. As I mentioned, we ran maybe 4 or 5 or 6 different types of curtailment requests. I'm just going to use the time I have to talk about one of them in particular. So what you see here is apparently a very famous or well-known type of demand spike. I myself was not familiar with it, but it's the tea kettle balance. And so in Europe, it is, I guess, a well-known phenomenon that a lot of people watching football or soccer, and halftime hits and everybody wants tea at the same time. And so what you see is actually a fairly predictable and well-known spike in demand that occurs at halftime as everybody gets up, takes a break from the game, pours themselves a cup of tea. Then they watch the second half, and then there's the game ends, a second cup of tea is warranted. And that is the call being sent by National Grid in this demonstration. And our software responds in inverse, right? So the demand spike, because of the electric tea kettles, is met with an inverse relationship where the data center is reducing demand. And so that black line you see there is the power target. So this is the request from the grid operator coming in, first requesting a 35% drop, then the second, following the second half, a 25% drop, first for 30 minutes and the second for an hour. Different demonstrations have covered different percentages and depths and hours held. But what you'll see here is something that is true across every single one of our demos, which is the curtailment response is never an amount that breaks that power target. In other words, this is perfect compliance, right, from a technical perspective. You'll also see that it's not just a instantaneous drop, because grid operators would prefer not to see that if at all possible. But that is largely because of wanting to balance the system, not because of a technical or a technological inability. There is another demo that I don't think I have a slide on where there was a simulated lightning strike where the response was much quicker. So that's what the grid operator sees. But if you look under the hood, this is what's going on at the data center, which is the data center is running many different jobs all at one time. And in aggregate, that results in that one single aggregated line that is easy for a grid operator to understand and see. And it's doing so in a way that protects ultimately the compute, because jobs at a data center, some are higher and some are lower priority. And so what Emerald does is we're able to identify what are the priority jobs, ones that are really important to the data center that they don't want, slowed or interrupted or affected, keeps those running as they would otherwise. And then for lower priority jobs that do lend themselves well to some type of flexibility, targeting those so that the aggregate, whatever it is, the 25, the 30, whatever the request is met. I promised that I would focus primarily on the demonstrations, but I can't help myself but show one slide in particular from policy. Here we go. So across the 5 demonstrations that we've done to date, as well as the work of many others in this space, for me, the key learning has been that the barrier is not technological or technical. It is policy and regulatory driven. In other words, there is data center flexibility available today at commercial scale. The barrier is instead in the nature of policy. And as somebody who spent his career in the regulatory space, this is entirely understandable to me. The innovation happens first, and then the regulatory update happens following. That said, I am eager to see continued update in the policy sphere. And here we've identified 4 things in particular that I think are important across any particular policy. Number 1, if we are in a moment of unprecedented demand growth, if we are in a moment of questions of access to the grid, then sizing the value to that moment is really important. In other words, building a expedited connection pathway for flexible loads is really important. Second is doing that in a way that adopts tech neutral standards. Here I think that the point is simply not to pick and choose winners and losers, but instead to focus on results and focus on performance. Third, benefit from the full value flexibility affords, which is a much longer conversation and worth, I think, quite fulsome review and deep dive. All I mean by this, though, at a really high level is neither a policy that requires no flexibility or all flexibility is workable for a program. Instead, something that benefits from a reasonable and achievable amount of flexibility that a data center or a large load can afford is really important to design a policy around. And using a market-based approach, like what we just heard a moment ago, I think is a useful and additional way to go about doing this. And then finally, I will just say, building on demonstrated models, there are a number from those being advanced in munis and co-ops and public power like Silicon Valley Power to larger ones across different ISO and RTOs, pulling out what works, replicating them, scaling them, building best practices rather than starting from scratch, obviously very important. So delighted to talk about any of those, any of the demonstrations or the UK demonstration in more detail, or about the policy positions I just shared, but I'm going to turn it over now to, I think, Gabe. Is that right? Awesome.
Green button.
There we go. All right. Hi, everybody. I'm Gabe Tabak, Head of Energy Policy at Verrus. And as Beth indicated, I'm here's Jeff Bladen's understudy. Many of you know Jeff. But glad to be here. And I will, I see a number of familiar faces from the panel I was on yesterday. So I'm not going to jump all the way to the end of the slideshow to run through what Verrus is, but I will give a quick rundown now, and then I'll jump into some of the materials here. So if you haven't heard of Verrus, we are a startup data center developer. Our senior leadership comes largely either from hyperscalers or legacy data center companies, with sort of the common thesis that there is a better way to do data centers and compute, in particular based on the energy design of the data center itself. So we just heard from Michael about sort of the software side of flexibility. Verrus has some of its own operating protocols and optimization pieces, but fundamentally what we're working on is the hardware side, which I think is a great balance here to talk about different ways to achieve flexibility for large loads. So what makes a Verrus data center different from legacy ones? A couple of things that I will point out. The first is sort of the internal electric architecture of each of the buildings. At a legacy data center, most often the rows of servers and chips are wired serially with each having their own circuit. That results in reservation of headroom for each circuit. When you add those things up, you end up with some amount of the nameplate interconnect to the grid that is functionally not available for compute. So if you had a hypothetical 100 megawatt connection with a historic data center design, you might get 65 to 75 megawatts, depending on the exact design of available compute for that. Verrus has replaced that sort of circuitry approach with what's functionally an internal microgrid, 34.5 kV inside each building, connecting each of the parts of the building dynamically and able to move power around rapidly, which results in less reservations. So our engineers can be more granular on this, but it's close to I think an 85 to 90% utilization of the utility nameplate. The way that some of our folks characterize this is that if a customer were to build 3 Verrus data center buildings, they would effectively be getting a 4th for free, just based on the additional compute relative to typical designs there. The other piece is that not just a purely co-located resource, but integrated with the electrical design of each of those buildings is 4-hour lithium ferrous phosphate batteries. So that is backed up on a 1-to-1 basis. So hypothetically, you could, if it were needed, again, full flexibility is probably not the desirable outcome where you're told to curtail 100% of the load, but you could, in theory, curtail 100% of the load, and there would be no workload interruption for those 4 hours, or usual battery multiplication here. You could do 50% for 8 hours or 25% for 16 hours, and so forth. So those are a few of the things that make a Verrus data center electrically unique, and I'll jump into what we're thinking about in terms of interconnection commitments moving forward into operations as we're working on getting hopefully our first couple of projects stood up in the near future. So all of this is based around the sort of fundamental thesis that it is better to do flexibility on the front end than the back end, and that having not that there cannot be some flexibility achieved with legacy assets, but it's all going to be a lot easier if you have something that is built to accommodate from the start, and that you go through the interconnection process and design your operational controls sort of baked in for both what the hardware is capable of, what the market rules are, what the local grid topology would require. Let's see, there we go. All of this should look pretty familiar to folks who've been through sessions here today. And this is, again, getting to the level of concern around load growth, resource adequacy, trying to balance intermittent renewables, the need for capacity to be at least partially dispatchable, and the importance, again, of planning them as reliability assets, as grid assets, as accounting for that flexibility from the start, not later on down the road. This is, I think, one of the interesting things that's come out of today for me. I think PowerGem used a version of this slide, and then EPRI also had a sort of related and but differently distinguished taxonomy of flexibility, because flexibility can mean a whole bunch of things in a whole bunch of contexts. And a couple of ways to think about this. Are there ways that from the grid perspective, there can be load reduction? Again, there could be, when there is from the grid perspective, load reduction, that could be because of time shifting compute inside the data center, and there's actual reduced utilization happening inside the data center, or it could be continuing off the battery, and there could be no interruption from the customer perspective, as well as location shifting. If you, in particular, if there are extreme weather systems and a fleet of data centers that are able to route workloads dynamically, or even hours or days in advance, that can really be helpful there as well. And this runs through sort of what asset-driven examples would be, and also what sort of the process and software examples would be here. So fundamentally, and I think this will bridge well with the folks from grid operators coming up right after me, are some of the questions about, is this going to be reliable? What commitments can a flexible load make upfront that from an operational perspective means that they can be dispatched when and how they're supposed to be? And then I think a related question, and glad that Yasser's here for SPP, thinking about compensation of resources. SPP has been pretty forward thinking on some of the large load interconnection services, and I'm particularly interested in the price adaptive load service that's sort of in the waiting room now for SPP. And all of these are sort of key questions. I don't need to dive into all of them, but I mean, will this be counted in IRPs, or will the flexibility help to offset what the capacity increases would otherwise need to be from IRPs? Something we heard about earlier today. Will it help to support RA, and is the performance measurable and verifiable? There's a lot of opportunity here for everybody involved. This is sort of a potential win-win-win for the utilities, for the grid operators, and for folks actually operating the large load. Obviously, ideally, we'd like to be able to monetize the capabilities here. That isn't necessarily a necessity. There could be the ability to participate in sort of brute force curtailment, but obviously moving into things that really turn large loads into actual market participants is really what a fully flexible large load is capable of, and the sort of thing that we're really interested in developing. So this is really summing up the first portion here, trying to build large loads that are flexible from the start, that can be dispatchable and valuable to the grid from the start, and move from being sort of a static or inflexible draw on the grid to an actual reliability asset. And I'll get into that a little bit more in the next section. So interconnection, more than just the process to get plugged into the grid, this really gets into some of the questions that we've heard today about how you do the planning, what questions you have to ask, and how flexibility changes those questions and those answers. And really what we're focused on is trying to demonstrate in a sort of asset-backed, empirical fashion that a data center is capable of being an active resource that can help to support grid reliability, again, instead of just being a 8760 draw on the grid. This is probably a little bit fine print, although you guys have a bigger screen than we do up here. But really running through what the attributes are for some of the NERC reserve products, and what a fully flexible, electrically modern data center would be able to contribute. All of these are not necessarily in these don't necessarily need to be in the market provision of these capabilities, but at least in the self-provision, where if and in some of those back slides, you'll see a reference to what's called StabilaGrid, which is the outgrowth of Verrus's work with National Lab of the Rockies, which demonstrates that in the sort of Dominion 2024 lightning strike circumstances that caused voltage issues and then multiple data centers tripping offline, this electrical configuration would have been capable of self-providing the ride-through capabilities that really are being thought of now at NERC and also in regional processes in places like the MISO Large Load Working Group. And again, this is stuff that's easier to do when it is built for it from the bottom up. There's a lot of data needed for these things. Obviously, the grid operator or the local utility is going to need to know what the electric characteristics are, all the elements noted here. They're going to need to know the operational characteristics. How quickly can a large load curtail? How long can it curtail for? What's the frequency of dispatch? What's the recovery profile? For a Verrus data center, very rapid on the curtailment because, again, the batteries are not just co-located, but really integrated into each of the buildings. The duration, usual battery math, again, up to 4 hours, but longer than that if it's not 100% curtailment. And then the dispatch and recovery, these are, I think, 0.25C lithium ferrous phosphate batteries. And the dispatch sort of runs from there in ways that I think are familiar to any utilities or grid operators that are dispatching batteries, but are probably just a little novel on the load side in terms of thinking about dispatchable load itself being sort of a new paradigm. And then running through some of the grid support characteristics, what the battery system is capable of, Any backup generation, our intent is really to use the batteries as the principal backup, but if there is any other at a particular site based on grid needs or customer needs, that is possibility, what the EMS capabilities are, and what the telemetry looks like for the grid. So I think I just ran through most of those, actually, jumped ahead by a slide. So ultimately, this is really about, again, that large loads being operated as grid resources, not only as passive customers. And sort of if we are able to provide the assurance of those things on the front end, what can the grid operator then be able to utilize on the back end once a data center is up and running? These are a lot of the, again, NERC reserve products here, trying to figure out the resource qualification and a lot of the elements I just ran through, as well as what the baseline methodology looks like, seasonal accreditation, which matters a lot in some regions, what level of visibility there is. And yesterday you probably heard me talk about what the visibility is versus what the dispatchability is. And these are things that are, again, familiar on the generation side, in particular for storage. Question, and FERC has really come down on generally letting batteries determine their own state of charge, but making sure that on the load side, the grid operator has full understanding and awareness of what the state of charge is and what the recharge period would be, so that they're making instructions that the large load is capable of meeting, and that all these things have the level of data. Again, this is stuff that, for anyone who's been looking at the NERC emergency action letter from a few weeks ago, all this should be pretty familiar there, and ultimately helping support the reliability requirements, make sure that there's contingency support and resource availability. And also on both the reliability side and the market side, non-performance penalties are something that a flexible load is able to handle. This is not dissimilar from things on the generation side for uninstructed deviation penalties, operating outside the expected parameters and the instructed parameters. If we have flexible loads that are capable of being market participants, figuring out what the right incentives and disincentives are to make sure that they are behaving the way they're supposed to is incredibly important. So these are sort of a set of recommendations here that I won't dive into all in chapter and verse on each of these, but I think these are elements that our engineers and ops folks are really prepared to engage in discussions with utilities and grid operators in places we might be building, and working to make sure there is understanding and comfort with the level of detail and telemetry that's going to be going back to the grid operator, understanding what the reporting obligations look like, how to measure it, how to verify it, and how to handle make sure that we are not just complying with, but actively helping support reliability and compliance. Finally, I know I'm getting near the end of my time here. It is worth thinking about what this can do in terms of shifting away from peak on the system. If there is effective use of the energy storage and how many hours a year, I know folks I've heard about this quite a bit, but if we're able to shift a Verrus data center demand away from those peak hours, then it functionally should allow for less strain on the grid, fewer upgrades needed before connecting, and this is all through effective utilization of the battery storage. A few more elements on reserves here, but I would refer folks to our StabilaGrid work with National Lab of the Rockies as sort of the validation of the fastest pieces here. That's really on the order of milliseconds to second response. From there, the spinning and supplemental reserves, the things that are in like the 10-minute range, are less complicated than the rapid frequency response. And fortunately, lithium ferrous phosphate is a pretty good chemistry for that type of use. All in all, this is the level of granularity that a fully flexible load is capable of providing, I think is relatively new from the grid operator perspective. And we're really working hard to make sure that the utilities and grid operators in regions we might be building are comfortable with all these elements and sort of seeing them provided on the load side, not just from market generation side resources. So I'm at time here, but I know all these slides have been cataloged and will be available after. I don't need to run through all of the compliance and control systems here, because as a lawyer, these are probably areas where I'll just get myself in trouble anyway. But overall, the goal here is for flexible loads data centers to be active grid participants, to be able to help support reliability and work closely with the grid operators and utilities to sort of change the paradigm around inflexible large loads to flexible and dynamic ones. So yeah, is Yasser up next?
No, I'm gonna,
Oh,
no, because I'm gonna ask both of you guys.
Oh, okay.
questions.
all right, Michael.
Do I need to turn it on? Or are you turning it on? There we go. Yeah, so you wanted to wrap up. And
No,
then
I'm just loading it for the next guy.
Oh, okay. Oh, scanning through all the, here's
Yeah, there
various
we go.
stuff, yeah.
All right, here we go.
So you wanted to skip over all the SCADA and data stuff, and I want to go back to it. And
Oh, okay.
I was, Michael, when you were talking, I wanted to ask you in terms of the UK demonstration project, give us a little bit more insight as to, if you can, as to the sort of what was that communication between your project and the National Grid? What, is it a SCED, the equivalent of a SCED dispatch instruction, and then you have to respond in a certain time? Describe that.
Yeah, let me answer that question in a couple of different ways, but let me sort of step back and I think agree with where the question is coming from, which is the ability to actually, from the grid operator perspective, what you're able to see on the load side is incredibly important to how you could both marshal the resources available to you on the load side, but also like how that interacts with existing structures. And so, for example, using like SCED as like actually treating load like economic dispatch requires a certain level of visibility, right? That's not the only way to structure a regulatory program, and some they're just not going to be available, right? It kind of depends on what the underlying architecture is, but that certainly makes available some techniques, some approaches, some designs, and you just need that sort of like baseline visibility to do so. So number one, I think agree where the question is coming from. But number two, as far as in the UK context, maybe the two things to call out is number one, because it was a demo, there was direct communication directly to the data center in question. From and maybe this is number two, from Emerald's perspective, there's not really like a human in the loop, right? It's sort of going directly and the signals being sent directly to the software, which is then responding. So it's not as if either we at Emerald knew what was coming, nor is there sort of like a manual step. And sort of like expanding that out again requires like the underlying visibility architecture.
Yeah.
Right. And so yeah, so so the secret sauce there is it's the system that's able to receive that circuit and then do magic things at the data center. Is that a fair?
We have two. Yeah, so I'll give you an example of another recently announced program that we're doing with Silicon Valley Power, where we're helping to support and enable the utility in that setting through a grid link program to give them access and visibility into the data center space, because again, the visibility is so important.
Okay. And so similarly,
Yeah, I mean, I think that on the hardware side, that a Verrus data center is, I think, validated as being able to respond dynamically in response to signals. And a lot of that very much depends on the local rules. There have been circumstances discussing with utilities where they have a standard form DR contract, which is a phone call 60 minutes in advance, which we can respond that quickly, but that's not maximizing the capabilities of what a fully flexible large load is able to do. So trying to get to the point where it is not just a literally called upon resource, but one that is dispatchable in the timeframes that matter, or will be able to behave predictably in the sort of operational timeframes that matter, that are not in the scale that a phone call from the control room is going to be helpful for, is really valuable. And that is sort of, I think, to Michael's earlier point, making sure that both the, I guess, the regulatory and the operational pieces are keeping up with what the technical capabilities are.
Yeah, go ahead, Yasser.
Yeah. Yasser, SPP. So first, thank you for the presentation from the both of you. And I'm encouraged by what I saw. So all the hallmarks of being good grid citizens, right? As talking about a lot of reserves and ability to be active on the grid. And that's very assuring for a grid operator. And visibility for a grid operator is really key, like having the visibility and the transparency, which is something that we're requiring as part of our design. I'll talk about it in a little bit. My question is, at what point do you see, so this is a conversation we have with various customers, is at what point is that visibility turning it into controllability too intrusive, right? Because there are different assets that you bring to the table and they're for different purposes, is my understanding. There's some right requirements and those sort of things. What do you think is a sensible approach to say, okay, well, these are the assets that I'd say these are good to participate, these are good to have some controllability aspect beyond just the visibility, and where should we draw the line and in terms of letting you all do the business that you need to do to be able to provide these services?
Yeah, Michael, if you don't mind me taking from the hardware side here, we're at this point we're not planning to register the integrated battery storage as a separate grid resource. So that, I think the sort of what that implies is that the data center itself would be instructed in terms of what the grid operator needed. And then we would be using the battery to comply with that. And there would likely be visibility for the grid operator into, is there sufficient state of charge for the data center to be able to respond when we tell them we need them to drop 25% in the next 10 minutes and be able to sustain that for the next 4 hours? Will the battery state of charge sustain that? But that probably would function more as an aggregate instruction to the load than a dispatch to the battery.
I'm going to answer that question in a slightly different and certainly less technically sophisticated way, as Gabe just provided, which is more to talk about program design. And that, in my opinion, right, it at a high level, structure a program design that is opt-in, that works back from what are the grid operator goals, right? Like what is the constraint that you're trying to solve, and do so in a way that is as market-based as possible. So if a large load, just like a generation resource, like if they can provide that value, there should be a pathway, and then build the compliance to ensure rigor in the system, and then you'll see participation. It's going to be sort of a gradients of participation that way, and that way you're not foreclosing upon some participants that would be able to otherwise provide. That way you're not leaving efficiency on the table.
Very good. That was
I have one question.
Yep,
Yeah. Sorry.
No.
Okay. So you said something really caught my attention, which was, the fact that you guys are using batteries, and it's going to be very important for the grid operators to have a visibility into the state of charge. My question to you is, as someone developing these systems, do you have a preference on what the control expectation should be if you don't have state of charge, but the grid operator wants you to curtail?
Yeah, I think a lot of that would very much depend on, what the agreement is for interconnection. And all of that is going to be informed from our perspective, and folks probably heard me say a version of this yesterday, by what the local grid topology is like, and these are things that we would want to address on the front end, ideally, what the historic frequency of demand response events is and their depth and duration and sequencing, and also what the type of expected workloads are and what the number of nines of reliability that a particular customer would need there. Those things sort of operate and need to be hashed out in the interconnection agreement and the service level agreement with the customer to make sure that if there is a possibility of those probably long tail distribution, multi-day summer or winter events, is there a path to using things like again, from our perspective, our goal is to have as little interruption to the computational workload as possible, but there could be circumstances having hardware flexibility is not at all preclusive of having software flexibility and being able to do things that might change the location or the type of workload or prioritization that could enable longer compliance with what could be a long tail event. But all that may be pretty situationally specific, depending on the grid conditions and the customer needs.
All right.
So it depends.
Yeah, sure. No, that's a great question. I'm glad you got that in, Luke. All right, let's switch over to Luke and hear from the RTO and ERCOT perspective.
Okay, good afternoon, everybody. My name is Luke Butler. I am on the operations side, like the title suggests. I mean, it's fair to say operations planning. Typically what my team looks at, like the name suggests, is resource forecasting, which includes wind and solar, conventional resources, and comparing that to, I guess, available reserves and margin. Is there risk in the upcoming days? And where I'm going to focus on in this presentation is really kind of like current day, maybe next day risk, and how we can see these large loads contributing to enhancing reliability or responding to signals that either the market itself sends or ERCOT dispatches. So I know you've probably seen several of these slides over these last few days. So I'm not going to get into the details, but just in terms of kind of how this fits into this presentation and what I was going to discuss, as most of you most likely are aware, ERCOT has a large capacity of wind and solar. And due to that, that's an increased uncertainty in terms of the overall availability of capacity, looking obviously anytime in the future. But as you expand out into that horizon, that uncertainty grows. And we're continuing to project that there's going to be a large increase in solar over these next few years, like we have been seeing in the past decade for wind and solar. I think this kind of captures it too. So I don't want to spend too much time here, but overall peak demand sitting at 85.5 gigs, which was set in summer. But if you look at the winter peak that we've had, which I don't think I have on this slide, it's not too far underneath that. And I think the good point that Gabe mentioned is something that we're all becoming much more aware of, is some of the riskiest kind of extending periods of needing response from loads or from other resources is in these winter periods where it's not kind of getting through the net load peak of the evening, but it's sustained across multiple days. Okay, I think you've also seen this slide. I just take a quick pause. I'm probably going to cover a little bit of what AG Springer talked about this morning if you were in that session. So trying to avoid any major overlaps there. But I think this slide was in his slide deck as well. But just want to, this highlights why we're here, right? As the explosion in large load growth, particularly in this case, showing that in ERCOT. And how does that load growth, how do we tie in that load growth into maintaining reliability? Are there options that these loads can participate in as a load resource? What does that look like? And then I'll get into some of the Texas legislature laws that were passed in Bill 6 and how ERCOT plans to implement those primarily in the kind of immediate future as what I'll be focused on, but talking about a new tool that we're developing now, which is a large load curtailment manager, and talk through how we're thinking about that. A lot of words here, so not expecting you guys to read all of this, but maybe a little more detail if you want to refer to it. But I'll cut to the chase, and I want to say I think I've thought about this a little bit before I came up here, but I think it's fair to say that ERCOT would not be against almost all large loads choosing to register as a CLR. I paused there just because of the comments made earlier that maybe having it's all or nothing is a fair point. Maybe there's issues with both of those, but I think the fact that a controllable load resource in ERCOT gives ERCOT the visibility to understand what that load consumption or reduction or increase will be in the next 5 minutes, since ERCOT is a 5-minute energy real-time co-optimized market now. But that allows us to position non-CLRs or just thermal fleet, since we also consider renewable change as well, to make up for that change in either consumption or wind ramp or solar ramp, and not be kind of flying blindly, looking at frequency and trying to respond to changes in frequency. So I think CLR is definitely the preferred approach for this. And becoming a CLR, and then I'm talking standard CLR. I know that AG did talk about PCLRs, which is a little bit, it's a subtype with maybe a few more requirements and SCED requirements as well. But for CLRs, this would allow them to provide ancillary services as long as they're qualified and can demonstrate that they can provide those services. Obviously, they'd be able to participate in SCED through bid to buy, SCED being the energy dispatch. And like I just to summarize it, I think that gives ERCOT the greatest visibility and the tool to maintain reliability. There's also non-CLRs. You'll see just NCLRs and protocols as well. Both CLRs and NCLRs do require telemetry, and it's required to be registered and have a QSC in ERCOT's qualified scheduling entity. So a few more, I don't want to say hurdles, but additional requirements if you do take that route, which I know is something to consider. But a non-CLR and NCLR can participate in ancillary services as well. I think, but typically what we do see NCLRs provide are more frequency-based response through the use of a high set under frequency relay, looking for low frequency events and responding very rapidly to those frequency events by disconnecting. I think there'd be some discussions about, what size load we'd want to see on this type of service. And I think there are requirements related to that, but NCLRs, CLRs, valid options that would give ERCOT greater reliability if we did see these loads participate in those. ERS, Emergency Response Service, is a little bit different. So these loads do not have the requirement to provide telemetry. ERCOT reviews their performance through actual meter data. So, and in emergency conditions, which would be, when ERCOT declares EEAs, that's when these loads would be responding or receive the signal to respond. The last one is actually not implemented just yet, but was approved. It's the voluntary early curtailment load. So I think this one maybe is a little bit different than the other three in that it's not something that ERCOT directly sees as a reliability. I'm trying to phrase this correctly. It's not something like ERS where we are waiting for EEA. I think the biggest benefit is that the transmission operators, if they do have loads in their areas that are these vehicles, or what we refer to them as, it impacts their load shed amounts and kind of the load ratio shed amounts that they are obligated to provide. So if a smaller transmission operator has a large load connected to their service area, if they're registered as a vehicle, their total share of a system-wide ERCOT load shed event would be reduced if that load was a vehicle load. Okay, so before I get into kind of how we're thinking about SB6 and how that relates to maintaining reliability, I think I wanted to just quickly highlight the way that ERCOT declares EEAs, because that's a very big part of the ability for ERCOT to curtail large loads that fit into specific categories that were called out in SB6. So just what I wanted to mention is what I'll be referring to for EEA triggers are based off of physical responsive capability, or PRC. There are other conditions that ERCOT can trigger EEA for, which are sustained low frequency periods and things like that. But focusing on the PRC aspect, because that will relate much more closely to what I'll be talking about. So PRC is the total capacity in the ERCOT system that can respond to frequency deviations. It's the headroom that's available. So in real time, ERCOT's watching this PRC, and so it's a real-time based trigger. So the real-time headroom that's available at that time, if it drops below certain thresholds, that will trigger ERCOT's response to declare an EEA, which is a little bit different than I think some of the other RTOs, ISOs that maybe do look forward in the future and can declare maybe EEA1 off projected conditions. So I wanted to make sure that was clear. So with SB6, so the graph on the right side is a little small. I'm going to The next slide is going to be blown up and I'll walk through that in a little more detail. But with SB6, ERCOT is now, we're implementing a large load curtailment manager tool that would give us the ability to meet the requirements called out in SB6. So there's specific categories that were mentioned in the language, which include large loads that interconnect with existing generation facilities. There's some details there on like the cutoff dates of those loads that apply and the generation facilities that apply. I'm not going to get into that, but so we call those SB6 co-located or net metering locations. And the other one is SB6 50% backup generation sites, which are large loads that have indicated that they have at least 50% backup generation at their site that does not export to the ERCOT grid or synchronize to the ERCOT grid. And so the language in SB6 calls out when and what conditions ERCOT can request these loads to curtail. Some of that specifics is still going through the language process, rulemaking process now. So I want to caveat everything that I'm talking through here, and then even the graphic on the right are examples of how we're thinking about this currently, and some of the things that we need to be aware of in terms of, at what point do we ask these loads to curtail? Is it because we're projecting emergency conditions? Is it because we're in emergency conditions? Those are the keys that I think will be discussed in the NPRR that's very close to being submitted, or protocol revision request. But for now, what I'm presenting is at least how we're thinking about it currently, or unofficially is probably the better way to say that. So blowing up that graphic on the right, what this is trying to indicate is that because most of these large loads, what we're hearing is it's not an instantaneous response to the curtailment request. There's a lead time aspect that we need to respect. So because of the language in SB6, it does state that we need to curtail these loads to avoid going into emergency conditions for at least one of these specific types. We need to be aware of how long it takes a load to curtail and can't wait until the last minute, or can't wait until we are in EEA. So what this graphic's explaining is that we now need to project potential EEA conditions. And what all goes into that, and that's kind of where my team gets brought into this picture, is that we now need to look at what's the available capacity. I'm saying 30 minutes because that's what's on the screen in this example. Could be something different. But what's the available capacity in 30 minutes? Well, that involves the solar forecast, the wind forecast, the load forecast. How many of these loads that are responding in our load forecast aren't accurately represented in that load forecast? There's all sorts. My point is, there's all sorts of error that potentially go into this calculation. And then when you throw in something like what was just mentioned, state of charge on it, and maybe there's an existing response on a load that was curtailed a significant amount, but the state of charge disappears during this 30-minute outlook. Is our forecast going to be, significantly off if something like that happens? So these are all things we have to consider. But what this example is trying to show is that if we do this kind of tiered approach of curtailment, each of our curtailment instructions should be considered from that point going forward, at least for right now, regardless if they actually have responded just yet. And that way we're not we ask someone to curtail, maybe they take an hour. Well, we should not just ignore that response request or that curtailment request. We need to consider it. So the blue line at the bottom is kind of that projected PRC, or not necessarily PRC, but available capacity margin. And as it drops and it goes below some threshold, with our look ahead study, we need to ask those loads to curtail. And we do those based off of the different categories that I mentioned previously: net metering and co-located net metering, and then the backup gen greater than 50%. And then the graphic continues to show kind of the worst case scenario where maybe that's still not enough. Eventually you get to traditional loads and large loads that don't fit these categories that would maybe be under transmission operator load shed agreements. So yeah, I guess that's kind of where I wanted to stop and just say that's how we're thinking about things. It's not a simple answer of just knowing which loads to curtail by a category or by ruling. A lot of this is going to involve improving our forecasting techniques and thinking of new ways to consider curtailment that maybe we've asked for, but we haven't yet actually seen materialize in operations. So With that, I'll stop.
Okay, thanks. I'm gonna, as Yasser's coming up, I'm going to ask you a quick question about, well, I have so many questions. Let me try to boil down to one. As you're thinking about implementing the requirements for various curtailment activities, keeping track, how will loads communicate to ERCOT what they can do, what their capabilities are, so that ERCOT can roll that in and figure out a pre-emergency curtailment plan? Are you still working on that, or you got some ideas on that?
So I am a step away from that process, but what I can say is I know that we are working on a system that will be very similar to our existing generation registration system, where these large loads would be submitting things like, do they have backup generation? How long does it take for the backup generation to turn on? I think we need to now ask for state of charge if it's a battery, maybe, capability, things like that. But yeah, it'll be a similar system to what exists for generation.
Okay, thank you.
All right. Good afternoon, everyone. My name is Yasser with the Southwest Power Pool. My role is a director of operations support. I think Ahmed started the trend earlier talking about ops planning and how cool it is to be part of ops planning, and ultimately, at least what I got out of it. So I did start my career in ops planning myself, and I worked in operations and then worked in market design for many years, and then kind of just bounced back and forth. I started working on this large load effort at SPP with a team when I was in markets. And so when it came time to work on implementing it, I went to operations. So why not work on the harder side of it? It seems like. Okay, what I'm going to talk about today is actually what I'm going to go through the framework that SPP has in place, who's been working on since last summer. And there are several things happening for SPP in this large load space in terms of policy. A few things have been approved by FERC, and we're implemented some of it. Some of it is in the middle of being implemented, and some of it is in the works, as Gabe talked about that earlier with PAL. So I'm going to talk about this, and I'll take any questions at the end. When we first started on this effort, it was clear to us that our stakeholders were asking for a few things, and we could summarize those things into all things speed. Speed to information. They want to know what it's going to take to interconnect and the costs and where they should interconnect, and then speed to market. And then they wanted speed to power, right? And so those are the three things that they asked us for. So what we've done in response is that we worked on definition of large load, and then worked on expedited interconnection process to give some answers to these requests, right? What it would take to interconnect, what is the cost to interconnect? And these processes are new processes. They're in parallel to existing processes. They're a lot faster, they're quicker, but we also didn't want to compromise reliability. So I'll talk a little bit about what those 90-day assessment studies look like. And then the second thing was the speed to market. Having been in a region, and most regions have been dealing with resource adequacy issues, SPP was no stranger to that. And so we thought that if we wanted to facilitate a speed to market into the SPP region, we needed to facilitate bring your own generation type model, right? There's not enough generation to go around for everyone, especially when we talk about these large loads that are, large in magnitudes. And so we've come up with this generation assessment. We call it high impact large load generation assessment, or HILGA. That's one of the other things that this project, we got really creative, being locked in a room for a few weeks on funny acronyms. So we come up with the HIL and the CHIL and the HILGA, and a PAL is a price sensitive load, and prior PSL was not fun enough. So we said price adaptive load to make it a PAL. So that's the speed to market. And then we said, okay, how do we facilitate conditional or speed to power? It takes time to build generation. It takes time to build transmission. So we said, okay, we can offer a path towards, at least getting some sort of non-firm like interconnection, like a conditional interconnection, as long as you're willing to live with certain conditions. And so that's the conditional service. That's why it's called a CHIL. It's conditional high impact large load service. And we have different phases of that. So we have the CHIL phase, and then there's a reason why we ended up with a price adaptive load, because there's limitations on who can be a CHIL and how long you can be a CHIL for. So I'll talk a little bit more about that. The timeline looks like this. So basically, a part of our large load effort is in production already. So we're taking interconnection requests for high impact large load. FERC just approved last week our CHIL filing. So we're going to start accepting or approving a request for chill started in July. And then we're working on PAL. We're working on price adaptive load. That's in the queue. That's SVP is gonna have a proposal out there sometime, I believe late this year, Q4 2026. I see Gabe putting me on the record there, but it is Q4 2026. So, okay. One of the things, so the first thing that was important for us to do is to talk about high impact large load, what it is, what is a large load, right? So we've come up with a definition with thresholds. And I want to mention that during this effort, we had a lot of operations staff involved in implementing this policy. It's largely an interconnection process policy, but we thought it was the perfect time to introduce operational requirements and things that operations need. And so, for example, through the definition here, we put requirements to register in the market, right, and have right-through requirements. That was non-negotiable for SVP, right? This is the time to ask for things if you're going to give things in terms of the region. Thankful for our large load customers and our stakeholders that were very amenable to that and worked with us to come up with a reasonable but a reliable solution to integrating these things. And then we would perform an assessment that's a 90-day assessment, right? That's pretty quick for at least for SPP standards. That's really quick. 90 days to give you a generation and a connection answer, 90 days to give you an interconnection, at least conditions, what you would take in terms of upgrades and all those sort of things. So 90 days was our commitment, and we're going to meet that commitment. We already are meeting that commitment. We have, by the way, 8,500 megawatts of high impact large load requests in the queue right now. And so as part of the 90-day assessment, we're not taking shortcuts in terms of reliability. So we're doing stability analysis, we're doing short circuit analysis, we're doing EMT screening, all these things to make sure that this thing's reliable. Like, these large loads are different than traditional loads, right? They show up differently. They have different attributes. They have different, they are different. And so we needed to make sure that we can actually sustain these things from beyond just a deliverability of electrons and energy, right? It's more than that. And so that's part of the 90-day assessment that we're doing. I want to talk about this matrix briefly. This is a good summary of what these services are, what the paths are. So a hill is basically a large load that is able to obtain firm service, full firm service, meaning that you have sufficient capacity, you have sufficient deliverability into the load. And then you have generation assessment. That's a HILGA. You can choose to bring your supporting generation to make you whole, essentially, from a net energy standpoint. And so we've come up with a framework that allows us to do that assessment, and then the condition that you're not going to put that generator so far away from that load, right? And the reason for that, obviously, is that we need to make sure that it's close to the load so we don't have to deal with deliverability concerns, right? It's all about, okay, be whole as close, as localized as possible. And then chill and PAL are what we consider our flexible intermittent policies that are in the works. So at least PAL is in the works. Chill just got approved. What you see in common on all of these, it's 90 days for all of these, right? And what you also see in common for some of them is that with the exception of PAL, chill and HILGA are path to firm. You can't be in that state for forever. Right. At the end of the day, we want the grid to be reliable. At the end of the day, we want to build a transmission. We want to have sufficient capacity. We want full market participation at some point. So we're offering an intermittent transitional path towards that firm. As we say, connect now and then start getting towards the firm path. Get in the queue for generation and a connection. Start working towards your firm up the transmission service. And so that's the one thing that you'll see for chill and HILGA, which is one of the reasons why PAL was born, because PAL wants to be in that state for forever. And so we added some other conditions for us that I'll talk about in a little bit. Briefly, I'll talk about the HILGA. So HILGA, there are two different paths for HILGA: behind the meter generator, or basically an adjacent generator. We call it local type structure, right? And you have to be within 2 buses with that load, right? It's basically, you have to be adjacent. What you'll notice here, since this is an operations panel, I want to talk about some of the operations aspects. You'll see that we are requiring visibility. We are requiring separate metering of these assets, right? So we want to know what the storage is doing, what the load is doing, what are they capable of doing. And we are requiring market participation. There is no added expansion of behind the meter, right? Behind the meter exists today, but there's there's a narrow scope for what behind the meter is. We're not expanding that. So if you're a generator that's behind the same meter of that load and you're supporting that load, but you're too big to be behind the meter, you're no longer behind the meter. You have to be market participating. And then there are some nuances. I'm not going to spend too much time on what that is, but they have to participate, and then they have to be dispatchable, and then the market will take it from there. And then what you'll see also through here is that path 1 and path 2. Well, path 1, you don't really get an interconnection service because it's behind the meter. It's not really jurisdictional. Path 2, you get what we call a limited interconnection service. And it's a load limited interconnection service, meaning that you can't just bring all the generators that you want. You have to bring just sufficient generation to serve that load. We don't want this to be a shortcut or a way to bypass the queue that exists today, right? So it has to be very intentional to serve only that load. Again, these are interim services, right? So you have to actually firm up. On the load side, you can be a chill. And what constitutes a chill? You have two things at SPP that you have to get. You have to get firm transmission service. And to get firm transmission service, you also have to be resource adequate. You have to have sufficient capacity, designated network capacity, we call it, to get firm service. And then you also have to be deliverable, right? You have to have full deliverability to the load. And if you don't have either one of those, you don't have firm service, and that makes you a chill. So you can opt to get a conditional impact chill service. What I'll note here about the chill is that it is curtailable. That's the condition. It's pretty simple, is that you're curtailable if you don't have your supporting generation. So basically you're net withdrawing. You are curtailable, and you're curtailable even if you have your supporting generation on a net impact basis. What that means is that we are going to capture what your generator is doing, what your load is doing, that's supporting each other, and any net impact on transmission, on capacity, we are going to curtail it. We'll curtail it before EA, we'll curtail it for transmission emergencies or for any transmission-related congestion. The other thing, and ERCOT gentleman talked about a little bit, is that for us, old chill will likely be curtailed in EA2. And the reason for that is we start to get into conditions where we actually need all the generation that we can get for all the loads. So EA2 is a cutoff for us where we start curtailing the chill, even if there is enough generation and so on. Okay. So more on the chill a little bit. Again, it's a transitional service. It is in place for somebody to actually take advantage of it, get the speed to power until they can get the firm services and they can get through the full process. Okay, so once we worked up the chills is limited in service. You have to have enough generation, and then we have customers and stakeholders that wanted something more than that. And they said, well, what if I just want to take advantage of the surplus energy that may exist at SPP? Certainly we have windows where we have just tons of wind, and we could use something to actually take some of that wind. So we came up with the price adaptive load. So the price adaptive load is designed to only be there when there is surplus energy and when there is deliverability. And how we are ensuring that? We're ensuring that by saying that you actually have to be price sensitive. You have to be a dispatchable load in the market. And not only that, we have to be a dispatchable load in the market, but there's a cap to what you can bid in for that load. You can't bid in $1,000 as your willingness to pay. You have to bid in something reasonable, and we're coming up with what that reasonable is. A big concern that we had from our stakeholders and our regulators is impact on energy prices, or what they call as impact to rates, right? It could impact rates. And so we wanted to mitigate some of that. And so chill, we said you have to bring generation, so you don't have a big impact. But for price adaptive load, if you're not bringing generation, we are going to cap to what you can offer. And you're not going to be able to say, I'm willing to pay $1,000 and make the marginal energy price $1,000 for everybody else. So that's essentially, PAL is what I think is a good compromise for you. Come in, you do your business, as long as their prices are favorable, condition is favorable in terms of surplus energy and so on, the load would be dispatched, and it has to be fully dispatchable. Why? We do think that there is a net benefit to having a framework like PAL. It's ultimately, if you add more load to the denominator, if you think about it from a transmission standpoint, because PAL is going to pay for transmission service, so you have more load that's going to pay for transmission service, existing infrastructure, so they can help pay for existing infrastructure. In return, they get some energy, surplus excess energy when it exists. So we think that's a good trade-off. And the stakeholders certainly think that. I hope they think that, because we're going to get in front of them here in a little bit and we'll see what they decide in terms of approving it. So in summary, I do think that everything that we've done here has a lot of operational integrity in terms of the assessment. There's some work that we still are doing to make sure that more of these loads that we get, the more complex our system is going to get in terms of stability concerns. And Ahmed talked about that a little bit earlier in terms of, okay, you do it in planning, in operations that you're doing something similar. How are you making sure that there was not a gap, and how are you going to true up that gap? We are working on that extensively, and we're hoping to finalize some of that stuff in the next couple of months. That concludes my presentation, and I'll take any questions.
So I did have one question for you, Yasser.